Let's do an example involving washers. So in example 5, we want to find the volume of the solid of revolution formed by revolving the region bounded above by the graph f of x equal to x and below by the graph g of x equal to 1 over x over the interval from 1 to 4 about the x-axis. So the first thing we should do is we should definitely draw a picture. So let me draw the y-axis like this. Let's have our x-axis like this. And, let's go 1, 2, 3, 4. And then we'll have 1, 2, 3, 4 like that. And let's graph the f of x equal to x in blue. So f of x equal to x is just going to be the line y is equal to x. So that's going to look something like this. This is the line y is equal to x. And let's graph the function g of x, that's 1 over x. So that maybe looks something like this. Maybe that comes like this. It's a reciprocal function. Something along the lines like this. This is our y is equal to 1 over x. Okay. And we're bounded on the left by x equal to 1. So that's actually also where these two curves intersect. And we're bounded on the right by x equal to 4. So that's this region here. And why do we call the region that we're rotating R? And we're going to rotate about the x-axis. So put a little loop on the x-axis like that. And let me just shade the region that we're rotating, since that's what I've been doing throughout this section. So let's shade this guy like this. Okay, so we've definitely drawn the picture. Okay, and we want to chop up perpendicular to the axis of rotation. So chop up perpendicular to axis of rotation. So what I'm going to do is, because my axis of rotation is the x-axis over here, I'm going to chop up vertically like this. So my slices are going to look like this. And I hope you can see that we have this little bit of thickness lying on the x-axis. So we want to decide, is it dx or dy? And in this case, our answer is it's going to be a dx. Okay. So second to last thing we want to do is we want to set up the integral. So let's do that. So when I set up my integral is going to be in terms of x. So I'm going to put a dx over here. My region of integration is going to be the smallest that x can be, which is 1, and the biggest that x can be, which is 4. I know that I want to take pi times the radius of the big circle minus pi times the radius of the small circle. And I hope you could see from looking at this picture that the bigger function is going to be the x function. So I'm going to write an x in for the first big radius. And the smaller function is going to be given by the green graph, which is the 1 over x. So this should be 1 over x is my r small, the small radius. Okay. So I guess the last thing we need to do is we need to integrate. So let's do this. We have the integral from 1 to 4. We're going to have pi of x squared minus pi of x to the negative 2 squared dx. I hope you could see that we can really factor out a pi. So we're going to be able to pull out a pi. And I'm just going to integrate term by term. So I hope you don't mind if I don't rewrite out that step of factoring out the pi. The antiderivative of x squared is x cubed over 3. The antiderivative of x to the negative 2 is x to the negative 1 divided by negative 1. And we're going to evaluate this from 1 to 4. So I hope you can see that a negative times a negative is going to give us a positive number. So now we just have to plug in the endpoints. So we're going to get pi times, plug in the 4, you're going to get a 4 cubed over 3 plus 1 over 4. And then when we plug in the 1, we're going to get it 1 cubed, which is 1 over 3 plus 1. And I will let you guys simplify this fraction yourselves at home, but this is the volume that we get, okay? So I haven't been mentioning units because we haven't talked about it too much, but the units for volume are always going to be cubic units, so let's just put units cubed, okay? So that's it for this video. All right, everyone, take care.